Testing 1, 2, 3. Testing 1, 2, 3. Okay, welcome back, everybody. Sorry, I can't keep. I'm trying not to laugh too much. Yes, I'm in Overland Park, Kansas. I'm sorry the class started late. Trying to look for a spot, can't find one. So I'll be bringing to you live from Overland Park, Kansas, from my car. So hopefully we won't lose too much. I got a full battery, so we should be okay. All right. So any questions?
You're frozen.
Am I frozen? Oh my goodness, I don't know what to say. It could be my connection.
Yeah, it's coming in now, but you were kind of cutting in and out.
Okay. All right. Maybe it's my connection. Let me close down some applications. Sometimes my bandwidth is a little slow. But
yeah, it says that your network bandwidth is low on my side.
Okay. Let me see what I can shut down here. So give me 1 second. Okay. Well, hopefully, yeah, because for some reason in the area that I'm in, I'm running off my hotspot off my cell phone, and I'm at 4G. Normally I got 5G, so it's the irony is I'm right next to Sprint, their campus here. I'm like, okay, guys, I wish I don't move you. So bear with me. I hope that at least you can hear me at least. If not, if there's a problem, I apologize. I wish there was something I could do, but I'm like I said, I'm stuck in a parking lot, and there's not much I can do. So I shut down all my additional applications. So I'm using bare minimum. So anyway, how about what can we? Any questions before I attempt to start here? If we get cut off, just bear with me. I would reboot and get it back online. Okay. Okay. So we were going to start with chapter 13. Okay. Hope you all can see that. This particular chapter deals with what is called stoichiometry. And basically, in a nutshell, it's a real fancy word, stoichiometry, but I use examples like this before to help you understand what's going on here. I mean, everyday examples every day. For example, a vehicle. As you know, you need, a 4-wheel vehicle, you need 4 tires per car. And so the stoichiometry in that scenario is that we use, what I'm going to do, I'm going to shut down my video. but keep the voice going, obviously, so at least that help with the bandwidth. Okay, so hopefully you can, obviously, can you still see what I'm sharing? If you can't see what I'm sharing, please let me know. Okay, got a 3 up, so I'm assuming everybody's good with it. So I shut my video down. That helped with the bandwidth, and hopefully we shouldn't have any hesitation. Anyway, as I was stating about the bandwidth and stoichiometry, stoichiometry. You know, a good example is a vehicle. You know, 4 tires per car. The stoichiometry in that relationship is there is 4 tires per 4 car. A bicycle, obviously, 2 tires per bicycle frame. Tricycle, 3 tires per bicycle frame, and unicycle, 1 tire per bicycle frame. So notice that in those examples, the stoichiometry can vary. It could be a simple 1-to-1, it could be a 2-to-1, 3-to-1, 4-to-1, or any ratio combination that you have, 2-to-3, 4-to-5, anything of the sort, okay? And the situation is, well, where does this stoichiometry come from? Well, that relationship comes from the balanced chemical equations that we've been doing, okay? We've been talking about balancing chemical equations as per defined by the law of conservation of matter. We have to say, if I start off with X number of carbon atoms in the beginning, I'm going to have an X number of carbon atoms at the end, okay? And that relationship, once we learn how to balance the equation, let me see if I can put it all together. You know, if you think about this, we started with the elements, okay? We talked about how some elements gain electrons, lose electrons. Then we talked about how compounds are made, specifically ionic compounds. So we took the elements and then created ions, both negative and positive. And then from those ions, we put them together in the proper ratio so we can write a formula. And then we started looking at these compounds, both ionic and covalent compounds in their respective ratio, okay? And now put them together and reacting them to form certain products. And then from that, we talked about balancing these chemical reactions and balancing, making sure we got enough of all the elements on both sides of the reactants and product side, okay? And so that created the coefficient, that number you put in front of the chemical that tells the coefficient. We need that information because we're going to use that relation. Oh, we also talk about the mole. As I mentioned, the concept of the mole, that I cannot go from grams of X to grams of Y directly unless I go to moles. And so we talked about how to convert those grams to moles. And then now, using the relationship of the chemical reaction, the stoichiometry, that coefficient, we can start now to calculate if I have X grams of A, how many grams of B do I need to get this reaction to happen? Or alternatively, we can go to the other end of the equation and state, okay, I need to make 100 grams of compound product B or product D, whatever it is. How much of reactants do we need? Well, I need to convert that grams to moles, and from moles go back to grams of whatever we're looking for, okay? And this stoichiometry, this coefficient, is related to these calculations because it allows us to go from A to B, okay? So we'll put it all together here in a bit, hopefully. So the mole ratio is exactly what I was just talking about, okay? So we have this reaction here with nitrous oxide in the presence of oxygen to give us nitrogen dioxide. It's been properly balanced. We got 2 nitrogens on the left, 2 on the right. We got 4 oxygens total on the left and 4 total on the right, okay? And so what we say is that we can put it in the following terms or words. We can say it requires 2 molecules of NO, nitrogen oxide, monoxide, and 1 molecule of oxygen to react and gives us 2 molecules of NO2, okay? Now, if we up the ratio of NO by a factor of 5, and now, basically multiply the 2 times 5, now we have 10 molecules, okay, of NO. Why? If I do that, I need the corresponding number of oxygen molecules. Since the ratio of NO to O2 is 2 to 1, I need 5 molecules of oxygen. If I start off with 10 of NO, okay, which then results in producing a total of 10 molecules of NO2. Okay, that stoichiometric relationship between the NO and oxygen remains. It's a 2 to 1 ratio. And also along with that is the relationship with the amount of product I make. And generally, when we're in the lab, we're not talking about molecules, saying, well, one molecule, this one molecule. We use the term moles, okay, in the real world, moles. So when we balance this equation, we can replace the word molecules with moles, because we now know, based on Avogadro's number, that 1 mole is equal to 6.02 times 10 to the 23rd molecules. And so that times 2 tells us how many molecules of NO are needed in this reaction. And there are 6.02 times 10 to the 23rd molecules of oxygen to generate 2 moles, or twice Avogadro's number of NO2. Okay. All right. The same analysis is with this one, with the following reaction. We've got nitrogen reacting with hydrogen to give us 2 molecules of ammonia. Okay. So replacing molecules with moles, now we say 1 molecule of nitrogen requires 3 molecules of hydrogen, which then produces 2 moles, I should say, not molecules, 2 moles of ammonia. That is the stoichiometric relationship between the reactants 1 to 3, but we also have the stoichiometric relationship between hold on one second, I needed my pen and I don't have it here. Bear with me for 1 second. I'm probably going wild here. Okay. So coefficients gives us the mole ratios. And what we mean by the mole ratios is that once we balance, and I've introduced this before, I said, look at the coefficient between nitrogen and hydrogen in this case. So it's 1 nitrogen per 3 hydrogens is that mole ratio, which I can write with nitrogen in the numerator, or alternatively, I can invert everything and say 3 hydrogens over 1 nitrogen, okay? Now, which coefficient we use depends on the equation. But remember that if we're going to use the one on the left, that means that we're going to be multiplying this coefficient by X something, okay, of hydrogen, because we want the units of hydrogen to cancel out. If we use the one on the right, we're going to be multiplying this by nitrogen, some value of nitrogen, because we want nitrogens to cancel out. Okay, so using these coefficients, we set them up like we did in the second equation, in the second chapter where we're doing conversion factors. Okay, all right, so, but we have to learn how to balance chemical equations. And that was that last chapter that we discussed is, with 6 types of chemical reactions. Some of these balancing techniques are a trial and error, whereas depending on the type of reactions, there's others have a stoichiometric. We have a systematic approach on how to balances. So go review those so you know how to balance the chemical reactions, because you need those coefficients to do the calculations. All right. So that being said, if we take this reaction where we have iron 3 oxide and the presence of carbon monoxide, it will yield iron plus carbon dioxide. Okay. So this is a good way to get rid of rust, because iron 3 oxide is basically rust. All right. That converts the iron oxide into pure iron. So looking at the stoichiometric relationship between reactants, we have the relationship of 1 to 3 right here. So we're looking at the reactants. Their relationship is a 1 to 3 relationship. So we can write that relationship in either one, the coefficient on the left or the factor on the right, okay? But not only that, let me change the color here. There is a relationship between the iron 3 oxide and iron. So that is another ratio, okay? And there's a relationship between the iron 3 oxide and carbon dioxide, which is a 1 to 3, okay? Then there is a mole ratio, a relationship between carbon monoxide and iron. You see that? So it's another ratio. And also between carbon monoxide and carbon dioxide. So I wrote that in green. So here we have another set of relationship. And then further down, the other final relationship is between the two products, which is the iron and the carbon dioxide. Okay, so once we balance a chemical reaction, we look at all the stoichiometric relationship between reactants and products, and even within products themselves. Because knowing that, we can utilize this relationship to do our calculations. So down the road, you may be asked a question like, okay, if I start off with 20 grams of iron 3 oxide, for example, can you calculate how many grams of iron I will make? And that being the case, the only concern is in this reaction is between the iron 3 oxide and the iron. And their relationship, which is a 1 to 2. Don't really care about all the other ones, just between what the question asked. And sometimes you could be asked the question of, okay, I'll need to make, 100 grams of carbon dioxide for whatever reason. How many grams of carbon monoxide do I need? So our relationship here is a 3 to 3 mole ratio, which is essentially 1 to 1, okay? But notice something, we're in grams. We're going to eventually convert that gram numbers to moles, and then looking at that relationship between the two that need to be addressed, then we can do the calculation. Okay, so right now we're just dealing with moles, and eventually, when we're in the lab, we're not, measuring moles. We're measuring grams because our balance doesn't measure in moles. So we need to convert the grams to moles, and then if needed, the moles back to grams. All right. So here the question is, how many moles of iron can be formed from 10.2 moles of carbon monoxide? Now, like we've been doing all other reactions, we systematic approach to determine what we're looking for. We're looking for moles of iron. That's what we're looking for, okay? And so obviously we're going to do some type of calculation. So that's going to be units of moles of iron, okay? Then it says, write down what we're given. And we're given 10.2 moles of carbon monoxide, okay? So we wrote down what we want. We wrote down what we're looking for. The relationship that we have to concern ourselves with is simply between the iron and carbon monoxide. It's between iron and carbon monoxide. That's it. We don't really care about all the other relationships because the question is only asking between iron and carbon monoxide. So we then look at the stoichiometric relationship between the two, which is the 3 to 2 ratio of carbon monoxide to iron. So obviously we're going to need a conversion factor here. We know we need iron, so that's going to be the numerator. And we know that carbon monoxide must be in the denominator because we wanted to cancel unit-wise to end up with iron. And so looking at the balanced chemical equation, we simply put in the coefficients and we stick those in there, which is the 3 for carbon monoxide and 2 for iron. Okay, check our units. Carbon monoxides cancel out, leaving us with units of iron, which is what we're looking for because that is what the question asked. Okay, and now simply it's a matter of you taking 10.2 times 2 divided by 3 to give you the answer, which would be, oh, this is all the relationship I just talked, sorry, jumped ahead, which would be 6.80 moles of iron. Okay, double check your units. Notice how that cancels, leaving us with moles of iron. So it's been properly set up. The mole ratio, stoichiometric relationship came from the balanced chemical equation. We don't care about anything else other than what the question asks, which are the two reactants. Now notice we're dealing with moles here. The logical step would be, which would be the next step, would be to convert the moles to grams. Okay. All right, let's clear this up. And let's take a look at the next question. Next question says, how many moles of iron 3 oxide? So we're identifying that. And that means how many moles? So we're looking for moles of iron 3 oxide. Okay, are needed to form 17 moles of carbon dioxide. So we need carbon dioxide and we need to make 17 moles. Okay, based on the question. So our relationship is simply between the carbon dioxide and iron 3 oxide only. Okay, so we write down what we're given, 17 moles of carbon dioxide. Okay, our conversion factor comes into play. This factor we're going to have, on average, going to have at least 3 conversion factors set up to get us to point A to point B. Right now, we only got 1, but this is the beginnings of the types of reactions that we're going to be, calculations that we're going to be dealing with. All right, I need moles of iron 3 oxide in the numerator and CO2 in the denominator. Okay, there's 3 for CO2, 1 for iron 3 oxide. Okay, check our units. Carbon dioxide cancels out, leaving us with iron 3 oxide units. Now you do the math, 17 divided by 3 to give you the numbers that we're looking for, which would be 5.7 moles of iron 3 oxide are needed minimum to make 17 moles of carbon dioxide. And this relationship is true whether you're making 17 moles or you're making 17 million moles. Okay, that stoichiometric relationship is true regardless of the quantity that you're making. You know, the chemist normally is the one that generates the equation, not always, but generates a general product they're making. And then it's the chemical engineer who understands chemistry, but also understands the engineering involved to move a ton of this over to point A to point B. You know, obviously we're in the lab, I only got to move 10 grams of compound A to someplace else. And the chem engineer has the problem of figuring out how to do that safely and efficiently. Okay, that's the main difference between the chem engineer and the chemist. Okay, so these are the type of calculations necessary, or we're going to be doing. The takeaways here is knowing your chemical reaction. Notice that we've been taking words, converting reactions in words, converting those into formulas, which gave us the chemical reaction. Then we balanced them out, and we have a chemical equation given. It could be like this, and then from then we go take the next step to do calculations. In this case, we're dealing with units of moles, so to demonstrate how this stoichiometric relationship works here. Okay. So an example here, we got sulfur dioxide, okay, reacting with oxygen to give us sulfur trioxide. Or to balance this, we can put a 2 in front of sulfur trioxide, which gives us 6 oxygens. And then if we put a 2 in front of sulfur dioxide, that balances our oxygens and also balances our oxygen and sulfurs, I should say. All right, so here, I jumped ahead of myself here. It says, how many moles of sulfur trioxide? So I'm marking what I'm looking for. Will form if 0.165 moles of oxygen react, okay? And so our only concern is between oxygen and sulfur trioxide. So I mark it up in my equation so I can keep track of, who I'm dealing with. Don't care about sulfur dioxide. They're not involved in this calculation. So I write down, as always, what I'm given, which is 0.165 moles of oxygen, okay? Obviously, I'm going to need a conversion factor here, which would be a stoichiometric relationship. Then I write down what I'm looking for unit-wise at the end, so I can keep track of my setup and make sure I'm going in the right direction. Okay, our relationship between the O2 and SO3 is simply a 1 to 2. Obviously, I want O in the denominator because I want oxygen to cancel, and I'm looking for SO3 in the numerator. Okay, I plug in my coefficients, which is 2 to 1, and so basically I'm going to have twice 2 times 0.65 to give me the number of moles of sulfur trioxide. So let me clear this up and bring the other one. So I need twice if, excuse me, if I start off with 0.165 moles of oxygen, I will generate 0.330 moles of sulfur dioxide. Okay, so bear in mind when these type of reactions that, we're only concerned about oxygen and sulfur dioxide. It is assumed that the other reactant, if there is a reactant, is there in sufficient quantity so this process can react. Okay. If it's not, then that quantity doesn't compute itself to completion. Okay. I had a point to make here, but no, let's go on to the next one. Let me clear this up. And next one here says, how many moles of sulfur dioxide, so we're talking about sulfur dioxide, are needed to make 0.042 moles of sulfur trioxide? So the only relationship that we're concerned about is between the SO2 and the SO3, okay? Notice the stoichiometry. It's a 2 to 2 relationship, which should tell you, hey, it's a simple 1 to 1. So whatever moles of one, it's going to be the same number of moles of the other, because the stoichiometric relationship is a 1 to 1, even though there's a 2 to 2 written, or 2 divided by 2 is 1 to 1. So we write down, as always, what we are given for 2 moles of the sulfur trioxide. We're looking for moles of sulfur dioxide. And so trioxide is being put in the denominator because we want that to cancel, and sulfur dioxide is put in the numerator. We go back to the equation. It's a simple 2 to 2. Okay, and notice that's why I said it's a 1 to 1, because 2 divided by 2 is equal to 1. All right. And so now my units of SO3 cancel, leaving me with units of SO2, which is what I'm looking for. And therefore, if I start off at 0.042 moles of sulfur trioxide, I will need the same number of moles of sulfur dioxide. Okay, but what I was going to say before was this: if we look at the previous examples, we were dealing with nice whole numbers. Okay, 3 to 1, so on, very big numbers. But here, we're dealing with, decimal numbers, small numbers. Regardless of where am I dealing with nice whole big numbers or small, less than 1 numbers, the stoichiometric relationship between reactants and products and reactants, or reactants and reactants, is the same. Okay, is the same. All right. So this brings us to this. Recall the last flow chart that we talked about. Kind of put down for you here. We had moles given. We needed to moles defined. We had to deal with the mole ratio. We also had that relationship of 22.4 liters per mole. And anyway, we're going to put it all together for you in one big flow chart. And when you're dealing with these type of reactions, I strongly suggest that you, until you get comfortable with them, with the type and comfortable with the way you're running with the reaction, follow the flow chart, because the flow chart will help you determine how you need to get from point A and point B. Because trust me, some of these reactions, I remember the first time I came and encountered them, I was totally lost, because there wasn't any systematic approach given. They just said, here it is, this is the way it happens. And no one really explained what's going on here. That's my attempt here to break it down stepwise. Now, I understand if you got it, that's great. You have a shorthand way of doing it. That's great. That's, more power to you. Congratulations. But there's some that maybe are still working through it. All right. So I'm going to just make the assumption that we're all at ground zero and we'll move forward from there. All right. So here's the deal. You start off with grams given in a problem. And I need to determine grams of either what I'm looking for. So let's say I got, 20.0 grams of A in some crazy reaction. I need to determine how many grams of X I need as one of the products, or how many grams of X could be one of the reactants. Doesn't make any difference, okay? But I do know this: if I start with grams, I got to convert that to moles. And if I have an element in grams, no problem. I just take the atomic weight and I'm good to go. I divide by atomic weight, right? Because remember, the atomic weight / molar mass has the units of grams per mole. Okay, which is a ratio which I can set up with as moles over grams. And depending on what the problem is, I'm going to use the one in the left or the one in the right. If I'm given grams, obviously I'm going to use the one on the right. Why? Because my grams are going to cancel, leaving me with moles, which is what I'm looking for. So I need to convert grams given to moles given, okay? Once I do that, I can go any direction I need to, okay? Because I cannot go directly from grams to grams given the problems that I'm going to be working with, okay? If I knew the total number of grams of reactant A, the total number of grams of reactant B, and I'm only make one product, then I know the total grams of product C. But if I'm making two products, I need to determine, well, maybe the ratio of those two products are different. So that's why I can't go from grams directly to grams. I gotta go to moles. Okay. Once I know moles, the next key important aspect is the mole ratio. That mole ratio, which comes from the balanced chemical equation, will give us what moles we're looking for. And that is what moles finds is all about. What are the moles of the product that I'm looking for, okay? And obviously, we don't work simply with moles. We work with grams, especially in the lab. So once I find moles of whatever I'm looking for, with its respective molar mass, now I determine the number of grams. And that's why I can go with the grams of X. Once I go through all these relationships, moles, molar mass, mole ratio, and the molar mass of what I'm looking for. Okay. All right, let me clear up my mess here. All right, so let's take this particular reaction here. We have iron 2 oxide, okay, specifically 3 moles, reacts with 2 moles of aluminum, which then gives us 3 moles of solid iron, elemental iron, and 1 mole of aluminum aluminum oxide. I almost made a big boo-boo there, right? Did anybody hear what that boo-boo was when I was naming this final compound here? Yeah, I almost call this aluminum trioxide, which is a big no-no, right? Because with ionic compounds, there's no prefixes. All right. Does not mean that marketing that they're selling this doesn't introduce the tri. That's a marketing thing. All right, so now here's our balanced chemical equation. Everything looks fine as far as being balanced. Okay, and I'm asked a couple of questions. All right, first question is this: calculate the mass of iron 2 oxide needed to completely react with 5.55 grams of aluminum. So what we're dealing with here is simply the reactants. All right, if I go out to the lab and I weigh out 5.55 grams of aluminum, how many grams of iron 2 oxide do I need? And we do that quite often when we're doing a reaction. Most of the calculations are are with my reactants. Once I have my numbers set up, then I can calculate how much product I'm going to make. Okay. But right now I need to figure out, well, all right, how much iron 2 oxide do I need? Now I could reverse it completely. I don't have to say aluminum. I could say if I start off with 5.55 grams of iron 2 oxide, how much aluminum do I need? That could be the question too. Okay. So that's the first question. We got 2 questions in this scenario. Second question is calculate the mass of aluminum oxide, which is here. So how many grams of this are produced when you start off with 10.25 grams of aluminum? So our only concern is between aluminum and aluminum oxide, which, note, is a 2-to-1 ratio. Between the reactants in the previous question number 1, note the ratio, it's a 3-to-2 ratio, okay? All right, so those are the 2 questions we're gonna calculate based on this reaction here. Let's take the first one, the reaction here. We got 5.55 grams of aluminum. Well, we're only concerned about the 2 reactants, that's it, okay? So step number 1 is we need to convert the grams to moles. And so since aluminum is an element, we just simply look up the atomic weight of aluminum, which is 26.98 grams per mole, okay? Notice grams is in the denominator because you're starting with grams, and unit-wise, grams cancel. Okay, and if we're to stop the mathematical reaction calculation here, we would end up with moles of aluminum. All right. Next scenario is we look at the stoichiometric relationship between aluminum and iron 2 oxide, okay? Because we're trying to get to how much iron 2 oxide. Okay, so from the balance chemical equation, it's a 3:2 ratio. Again, keeping track of your units, knowing that I have to put aluminum in the denominator because I want to get rid of aluminum and get to iron 3 oxide, because that is the ultimate goal. That is how much, that's what the question asks for. How much aluminum oxide do I need? Aluminum 2 oxide. And finally, notice here, if we stop the mathematics at this point, unit-wise, we end up with moles of iron 2 oxide. Okay, but the question asks to how many grams of iron 2 oxide. So the next step is to get the atomic weight, or in this case, molar mass, because it's a compound, of iron 2 oxide. We look up the atomic weight of iron, the atomic weight of oxygen. That should tally up to 71.85 grams per mole. Okay, all along, keeping track of your units. Okay, and obviously don't lose track of your sig figs, but in these 3 conversion factors, none of them would have an effect on your final sig fig numbers. Only the first 5.55 grams is a measurement. Everything else would not be used. Okay, so with that, checking my units end up in grams of iron 2 oxide. Now I can do the mathematics. And someone asked me a while back, and I may have mentioned it, but I'll do it again. In your calculators, does it make a difference if I, multiply all my numerators and then multiply all my denominators and then do the math at the end to get a number? And the answer is no, but you don't have to do that. Most calculators, if you type in 5.55, hit the divide, and then input 26.98, then hit the multiply, hit 3, divide, hit the divide by 2, then hit the multiply by 71.85. You should get the correct answer. To double check that your calculator follows the rules of the mathematics in that process, what you do is you type in 5.55, then the divide 26.98, then hit the equal. Okay, then hit the multiply, the 3, then hit the equal. Then the divide by 2, hit the equal, and then finally by the multiply by 71.85, then hit the equal. If both processes in your calculator are the same, then you don't have to hit the equal each time. If not the same answer, then your calculator more than likely does not follow the mathematical functions properly. So check your manual to see how to make sure you're doing it properly. Okay, because I've had some calculators where you do follow the sequence and your answer is, I don't know, it's not the correct answer. Okay, so verify it, doing it both ways to make sure that you are doing the proper mathematics. Okay, that being the case, we plug it in. You should end up with 22.2 grams of iron 2 oxide. Okay, so what does this mean? All right, this means the following. That if I start off with 5.5 grams of aluminum, I also need 22.2 grams of iron 2 oxide. Okay, for this reaction to proceed in the proper ratio to give me a proper amount of product. Now, if I use less than 22.2 grams of iron 2 oxide, would the reaction proceed? Yeah, it will, but you won't make as much product as, you will not maximize the amount of product that you can make. And the same is true. Yeah, if I add too much, more than 22.2, you're still going to make the amount of product you need to make. Okay, what governs there depends on the amount. Another way to look at this is the following. Let's say you had, we know that this is my example of a bicycle, okay, with no frame. Okay, so I'm not an artist, so bear with me. All right, we know that I need 2 tires to give me one frame. 2 tires gives me 1 fully assembled bicycle. It's a crude picture here with my tires, okay? All right. Now, if I start off with 10 frames, obviously I need 20 tires, correct? Which would then give me 10 assembled bicycles. But if I start off with 10, but this time I have 21 tires, well, I'm still going to have 10 assembled bicycles, but I'm going to have 1 excess tire left over, right? You see that? And the other way around, if I start off with 10, but I only have 19 tires, obviously I'm not going to have all 10 fully. I'm only have nine assembled bicycles. Okay, so in order to make the right amount of product over here, the amount that I calculate, I need at the minimum, I need 22.2 grams of iron oxide, 5.5 grams of aluminum. If I add too much of one or too little of the other, that will change the final quantity of both the iron and the iron oxide. Okay. All right. Now the second part was we need to make how much, I think it was iron 3 oxide based on 10.2 grams of aluminum. Okay. And so we're concerned here is about aluminum and aluminum oxide only. And that relationship is a 2 to 1. So we start off with 10.25 grams of aluminum. Obviously, for step number 1, take the grams, convert that to moles. Okay, so we need the atomic weight of aluminum. Okay, then we need the stoichiometric relationship between the aluminum oxide and aluminum, which is a 1-to-2 relationship. That's based on the balanced chemical equation. And then finally, once we know that, knowing the atomic weight or the molar mass of the final product, we can calculate how many grams. And so that becomes 19.37 grams of aluminum oxide. So if I start off with, another way to say that is if I start off with 10.25 grams of aluminum, I'm going to make 19.37 grams, assuming we have the right amount of iron 2 oxide. Okay. All right. So here is the flow chart, the complete flow chart here that puts everything together. This is the flow chart you should utilize when you're doing these calculations, all right? So what we just did was start from grams given of some material, and we're looking for grams fine of some product or another reactant, who knows? But regardless, we needed to get to moles. So we need the molar mass of the compound we're given. This comes from the balanced chemical equation. Once we know that, that tells us how many moles we're looking for, okay? And once we know the molar mass of that material, we can figure out the mass. If you're told you are at STP, remember only at STP, we can use this relationship. So if one of your products is a gas, we can calculate the volume, okay? Because of this relationship right here, which we talked about before, okay? All right. So, or we can go the other direction. We can go in this direction down here from grams given to maybe it's a gas. We need to figure out the volume of it, okay? And basically too, it's you can work backwards. One thing about all these problems, you go one direction, you can also need to be able to go from one direction to the other. So this could be an example of, I need to make 100 grams of some compound X, how much compound Y do I need over here? This is for Y. All right, so I'm going in this direction. But regardless of which direction I'm going to, I need to convert everything to moles. And then if it's a chemical reaction, then based on the mole ratio between the two reactants or the species we're looking for, we can get 2 moles of what we're looking for. Okay. So this flow chart will, if you follow it, identify where you started and just follow it through. It will help you in determining and figuring out the problems that you need to be calculating. Okay. All right. Here's an example. We'll do a couple examples and then we'll be done with this one. They're asking you, write and balance the reaction of hydrochloric acid and cobalt. Okay, now, if you look at the activity series, you will find that hydrogen, cobalt is a lot more reactive than hydrogen, and cobalt is in elemental form, therefore reaction proceeds, okay? So basically what we're doing here, and they're telling you something else, you don't have to do that in activities because they're telling you here. So no, cobalt will be in the +2, all right? So that they're telling you it's gonna be a +2, and we need to know that because remember, cobalt is not part of the 16, doesn't have a constant exact oxidation number. So we need to be told it has a variable oxidation number. All right. So we write the reaction down. And so we have cobalt, which is a solid, okay, in the presence of hydrochloric acid, which is aqueous system, okay? And this reaction will proceed. It's a single replacement reaction. We're going to replace the cobalt with the hydrogen and generate H2, okay? Then you're told we're going to be in the cobalt 2 position, oxidation number, I should say. And here's the anion, which is chloride. So we're going to need 2 chlorides for every cobalt. And so we have cobalt Cl2, okay? Which also will be soluble based on the solubility rules. It's a chloride, will be soluble. Okay, now we got to do is balance it. And if we stick a 2 in front of HCl, guess what? That's pretty straightforward because we got 2 hydrogens here, 2 on the right, 2 chlorides in the left, 2 Cls, 2 Cls on the right, 1 cobalt on both sides. It is balanced. Okay, so let me write the reaction. Uh-oh. This is fun lecturing in my car. All right, so here we got the balance given equation. Now you're asked the question, okay? How many liters of gas at STP will form if 5.0 grams of cobalt reacts? All right, so let's mark all the important information that we're looking for about how many liters of gas. Well, obviously, hydrogen gas, we're asking how many liters of gas are being formed if 5.00 grams of cobalt reacted. So our only concern is between cobalt and hydrogen gas. That's our concern, okay? So that being the case, and also, before I forget, we are at STP. So what does that tell us? That if needed, we can use the 22.4 liters per mole relationship. And it sounds like we're probably going to need it here, okay? So we're trying to calculate how many moles of hydrogen gas based on 5 grams of cobalt, and that we are at STP. All right. So we write down what we're given, as always, okay? Nothing here. Since we are in grams, guess what? We need to convert to moles. We can't go any further without converting it to moles. So looking at cobalt is a element, we simply look up the atomic weight, 58.93 grams cobalt per mole, okay? That gets us into moles of cobalt. Now we need the stoichiometric relationship between cobalt and what we're looking for, which is hydrogen, right? And that comes from the balanced chemical equation. It is 1 hydrogen per 1 cobalt. We put hydrogen in the numerator. Why? Because that's what we're looking for. That's defined. So keeping track of your units. Let me change a different color here. We got cobalt, grams of cobalt, balance, canceling out grams of cobalt, moles of cobalt, cancel out moles of cobalt, leaving us at this point, if we were stopping the calculation, with moles of hydrogen. But the question wants us to calculate the number of the liters of hydrogen. So therefore we need to get 2 liters. And since we're at STP, we use the 22.4 liters, and that gives us almost 2 liters of hydrogen gas, 1.90. So if we start off with 5 grams of cobalt, and we are at 0 degrees Celsius and at 1 atmosphere pressure, we let this reaction proceed, we will generate and create 1.90 liters of hydrogen gas, okay? Next question says, if 2.374 liters of hydrogen gas is formed, how many grams of HCl reacted? Okay, so going back up here, this tells me, I always like to write on the equation because that really kind of keeps track of what I'm doing, what I need to do. So 2.374 liters of hydrogen gas was created and formed, reacted, and that was analyzed. They need to know that we need to know how many grams of HCl reacted there. So that's a relationship that we need to deal with between HCl and hydrogen, which is a 2-to-1 relationship, okay? Okay, so 2.374 liters of hydrogen gas. Okay, we can convert, we're still at STP. And so 22.4 liters per mole, okay, that converts us to moles of hydrogen. Okay, now we're good to go. Now we can go to moles of HCl because we know the relationship, stoichiometric relationship between HCl and H2 is a 2-to-1. Okay, once we know that, we simply go to grams by determining the molar mass of HCl, which is 1 chloride, 1 hydrogen, gives us 36.46 grams per mole. Okay, before you do anything, double check your units. Make sure that your units are canceling. Liters of HCl, liters cancel, moles and moles, moles and moles, leaving us with grams of HCl, which is what the question asks for. So you know you got that set up properly. Now you got to do is simply do the mathematics, and you should end up with 7.72 grams of HCl. Now, 7.72 grams of HCl have 3 sig figs. 2.374 liters of HCl has 4 sig figs. So why does our answer only have 3 sig figs? Is that correct? Should our answer have 3 sig figs? Yeah, and that is correct. Why is that? Because remember the 22.4 liters is a measurement. And being a measurement, it can be a factor in determining your sig figs. And that has 3 sig figs. Your 2.374 has 4 sig figs. So the 22.4 determines the number of sig figs that you're going to have in your answer. Okay. All right. In this particular reaction, we're going to kind of put everything together here because they're asking you to do the following. You're given the reaction, okay? You're going to have to take that, what you're given in words, and convert it to a chemical reaction. So what we have here is the following. We have hydrochloric acid, which is, something, HCl gas plus oxygen gas, remember it is diatomic, produces chlorine gas, okay, plus H2O, also in the gas vapor, okay? So you can do this any multiple ways as far as balancing. 6 1/2 dozen or the other. I don't know. You can see, you can notice I got 2 oxygens on the left. Unfortunately, this is a trial and error type one of balancing. I can start by putting 2 oxygens here in water to kind of balance my oxygens. I got 2 on the left, 2 on the right. Okay. Now, if what that did was kick up my hydrogens, well, what if I put a 4 there for my hydrogens? That takes care of hydrogens, but that kicks up my chlorides. So if I do 2 here, doesn't that correct my chlorides? I got 4 on the left, 4 on the right. I got 4 hydrogens on the left, 4 on the right. I got 2 oxygens on the left, 2 on the right. Okay, that looks balanced. Okay, and so we end up with the following. Take out my mess and we'll give you that. Okay, we got balanced chemical reaction. The relationship between HCl and oxygen is a 4 to 1. Okay. Question could be asked, was asked, how many liters of chlorine can be formed if 3 liters of oxygen are needed to completely react completely at STP? And so how many liters of chlorine can be formed if 3 liters of oxygen were used? So we're looking between the relationship between O2 and Cl2, which is a 1 to 2 relationship. Okay. So we write down what we're given, 3 liters of oxygen. Okay. We are at STP, which is 22.4 liters per mole. Okay. The stoichiometric relationship is a 2 to 1 from the balanced chemical equation, 2 chlorine to 1 oxygen. And then that puts us back into moles of chlorine. So we want to get that back 2 liters, being that we're still at 22.4, we can put that back in. And so now our answer is 6.02 liters of chlorine. Now, if you notice something here, guess what? My factors of 22.4 liters can cancel out if, only if I'm working with gases in both scenarios, whichever react, if I'm working with whatever two entities I'm working with, they both have to be in gases. And second of all, of course, they have to be in STP. Okay. And with that being said, if I'm at STP, whoa, okay, notice what happens to the 22.4 liters. They by default, they cancel out. Okay. And so I can simply use my stoichiometric relationship directly to determine how many liters of whatever product or reactant I need. Okay. But only and only if everybody involved are gases and you are at STP. Because note that the 22.4 liters will eventually just cancel out, just by default. Okay. All right, try these at home. We can try these on Thursday again. Carbon reacts with oxygen to form carbon monoxide. And so you got to take that reaction, carbon reacts with oxygen to form carbon monoxide. Write out the equation, okay, balance it out. And then from the following questions need to be calculated. How many liters of carbon monoxide at STP can be made from, if scenario number one, you have 15 grams of carbon, and in scenario number two, if you have 20 liters of oxygen, okay? You should end up with 28.0 liters of carbon monoxide for the first scenario and 40 liters of carbon monoxide for the second scenario, okay? Let me show you, there it is, but let you work it through. So overview of the calculations. One, we took the elements and we created compounds, be it ionic, be it covalent, okay? From the compounds, we then reacted them with each other to form reactions. There's 6 different types of reactions, and we learned how to balance reactions and talked about the concept of balancing the chemical reactions. From the balanced chemical reactions, we now determine the stoichiometric ratios between reactants with each other, reactants and products, okay? That information that helps us and assists us in calculating the reactants or products based on these ratios, and we can do the calculations in terms of moles, grams, or in liters if we are at STP, okay, standard temperature and pressure. And this flow chart is the one that really needs to be kept, and so you can utilize it whenever you need to do your calculations, okay? You have grams in the far left, and you maybe want to get to volumes in the bottom right corner. The important thing is this. You can't do any of this directly without getting into moles, okay? You've got to get into moles before you can go from point A to point B, okay? And once you get that into moles, you're going to either do that by using the molar mass, or you're going to be using the mole ratio of a chemical reaction, okay? Or if you're at STP, you know, you can get into moles, but you also get the volume that you can calculate in terms of liters. Okay. That being said, ladies and gentlemen, that ends chapter 13. All right. So let me stop here. What we got? I think I'm 2 hours ahead of you. Where am I? Where am I? I don't even know where I'm at. No, I'm at almost 4:43 my time. I think you are at 2:43 your time. Back in Phoenix, right? I understand you got pretty hot back there. 100 and something.
Yeah, definitely hot here.
Not too bad here, but it's very humid. I lived here for like 30 years and I don't miss it. It's just too humid for me. Okay, well, I tell you what, let's take 15 minutes I got to run on here and take a look at my granddaughter. She's playing soccer. So let me run in there and take a look, see how the game's going along, and then we'll come back. I got 4:43 my time, which will be 2:43 your time. Let's call it 3 o'clock, 15 minutes. And then you got 112 by you? Oh, my clock that far off? Nate says it's brutal out there. You know, they tell me it's a hot heat. No, it's not. It's hot. It don't make a difference if it's dry heat, I should say. Wait, I've been in the hot jungles in Vietnam. That's hot. Hot Arizona. That's hot. Hot Kansas is hot. Doesn't make any difference. Okay, I got 245. So, Eduardo, I don't know. Oh, you got 112. Sorry, I was thinking it was the time. Sorry. All right, so let's come back at 3 o'clock. Okay, 15 minutes. All right, hoping my battery won't die. I think we'll be all right. Let me pause it. I'll be back in a little bit. Okay, and I'm back. All right, so just a quick reminder, I did forget this, but you know, this is next week is the final week. In fact, next Thursday is the final. So we just got done with chapter 12. I'm going to do 13 next, I believe. Make sure I got the right chapters. No, 14. What am I doing? Ended 13. 14, another one. A little bit more involved with that. We did get a late start. I'm going to see if we can get as much as we can before I run out of my battery, because I'm getting about halfway done. So if I lose contact, then we just cut it off there, and then we'll continue on Thursday. Thursday, we should have a more stable place. Okay. All right. And then after I'm done with 15, the following Tuesday, we'll do the last chapter again. Be pretty short. So I think that's all I had. All right. Okay. Well, let me share with you chapter 14, which deals with what are called intermolecular forces. Okay. Intermolecular forces. Now, the important part about this chapter to grasp, to understand, is you go back and review polarity, meaning looking at the compound based on the Lewis dot structure to help you out, then based on the bonds, determine whether a compound is either polar or nonpolar. Keeping in mind that in general, for compounds that have all nonpolar bonds, you're going to end up with a nonpolar molecule, okay? Now, if you have a compound that has all nonpolar bonds or polar bonds, and they don't cancel out each other due to the geometry, then you have a polar molecule. If those polar bonds cancel out, then the net polarity of the molecule is nonpolar. Now, we need to know that because we're going to assign to it, based on the polarity, a particular intermolecular force. Now, what this intermolecular force is just, if we think about it, it's the interaction between molecules, the interaction of molecules to have with each other in solution. Okay? Not within the molecule itself. Within the molecule, that would be called intra, I-N-T-R-A. And that would encompass what type of bond, be it an ionic bond, be it a covalent bond. Okay? And intermolecular forces, these deal with molecules interacting with other molecules. And that type of interaction, it could be a very strong interaction or a very weak interaction. The result is that has an effect on the properties of that compound. Okay, so with once we understand the polarity of the molecule, we can assign a particular intermolecular force. There's only 4 of them, okay? There's only 4 forces. And with that information, then we can do a compare and contrast of compounds. And we can look at specific physical properties such as things like boiling point. And we can, if we look at 2 molecules, we can ask the question, who has the higher boiling point or who has the lower boiling? That is answered by the intermolecular force that that molecule has. If it has a very strong intermolecular force, its boiling point will be much higher. Why? Because those strong intermolecular forces are these forces that keep these molecules together relative to each other very strongly. And if it's very strong, then it's going to take a lot of energy to break them apart to get them into a different phase. Okay. All right. So let's go on with this. So this diagram talks about, kind of demonstrate the intermolecular forces. Okay. Now here's 2 hypothetical diatomic molecules. Okay, denoted by the blue color. And I'm getting that my internet connection is a little bit unstable. Okay, that's back to normal. Okay, so what we have here are 2 molecules. And what we're dealing with is this dotted line here. These are the forces. That dotted line denotes the forces that molecules have with each other. Hence the intermolecular forces. In contrast, we have the intra, and those are the forces within the molecule, okay? And those forces will be what type of bond it is, basically. Okay. Now, as far as strength, the intermolecular forces are by way no means stronger than bond forces at all. They're not. They're strong, but not as strong as a chemical bond, okay? All right. So review polarity, nonpolar and polar bonds, and molecules, because that's going to be important here in defining the forces. So we have, for example, hydrochloric acid, okay, HCl, we denote here by the formula HCl. The blue dotted line in the bottom, we know that for one, the intra-force is that bond between the carbon and the hydrogen. And that would be a polar covalent bond. We also have a non-polar covalent bond if this was, say, hydrogen gas, right? Okay. But the intramolecular forces, that is represented here by the dotted line here at the bottom. How HCl interacts with another molecule of HCl, how strongly they interact. Okay? Those are intermolecular forces. Now, there's 4 types of intermolecular forces. And we'll denote that here with the, recall the partial positive and the partial negative. It stands to reason if you think about it. Remember the polar bonds, we had the polar arrow where we had a partial negative and a partial positive side. Why? It stands to reason if you have that type of molecule that these partial positives and partial negatives are going to line up with other molecules. The negatives are going to be attracted to the positive side, you know. So there's an interaction going on there that these molecules will have with each other. Now, the first type we're going to talk about are called London dispersion forces. They are by means the weakest ones. Okay. Any molecule that are nonpolar, any nonpolar molecule that is classified as nonpolar, that would mean things like any molecules with nonpolar bonds like carbon, hydrogen, any molecules that may have polar bonds, but they cancel each other out, resulting in a nonpolar molecule. Okay. Any of the diatomic molecules, all those guys, all those chemicals, the only force they have to deal with are called London dispersion forces, which are by all means, the weakest forces, okay? The next one, which is a little bit stronger, are called the dipole forces. Now, those are molecules that have a dipole. Recall the HCl example we just talked about, okay? There's a partial negative there and a partial positive on the hydrogen side. Well, relative to another hydrochloric acid molecule, because it also has a partial positive and a partial negative side, well, the partial negative attracts the partial positive. There's an interaction going on here denoted by the dotted line. We have a dipole, right? There's a dipole going, remember the dipole arrow going from the hydrogen to chloride in both of them. There is a dipole there, and hence dipole-dipole. It's like magnets lining up with each other. You get a bunch of magnets, they all lined up, north to south, etc. Okay? So those are dipole-dipole forces. Then we have a third type called hydrogen bridging forces. They also used to be called hydrogen bonding forces, but the term is not really technically correct because it's not really a bond, it's an interaction. And so they're trying to get away from using the term hydrogen bonding. And you may still find literature out there that talks about hydrogen bonding, but the preferred term is hydrogen bridging force, okay? Now, it's very specific here. Yes, they are a dipole-dipole interaction, but it's very specific that this type of bonding only occurs for three types of molecules. That is hydrogen bonded to nitrogen, hydrogen bonded to oxygen, and hydrogen bonded to fluoride, okay? Only those three examples exhibit the hydrogen bridging force. And between 1, 2, and 3, 3 is by all means the strongest force, and number 1 is the weakest force. And then somewhere, number 2 is somewhere in the middle, okay? These are just relative forces. So the thing about number 3 is, and I repeat, yes, it does have a dipole between the hydrogen and nitrogen, between the hydrogen and the oxygen, and the fluoride. But because of the nature of the beast, because of the hydrogen interaction with those specific elements, there's an additional force that's even stronger than the regular dipole-dipole, and that is called hydrogen bridging force, okay? And then finally, the last force is called the ion dipole force. Now, what this is, when you see the term ion, obviously you're thinking, you should think about an ionic compound, okay? And generally, when we deal with ionic compounds, pretty much all the time, we are dealing with an aqueous system. And so if it's an ion like sodium chloride in water, well, the only force involved there would be ion dipole forces that keep the molecules together in there. That's about it. They wouldn't exhibit any of either 1, 2, or 3. Okay. Ionic and water have their own little special force, and that's called the ion dipole force. All right, so dipole forces, or I should say dispersion force, not dipole, dispersion forces, or the London dispersion forces, are fairly much temporary forces. They occur between nonpolar molecules, okay? And they kind of form when these nonpolar molecules kind of get close to each other. Now keep in mind, we have electrons. We're talking about the electron interaction outside the molecule. This is where all the action's happening. That's all, okay? So these electrons come close to another molecule that have also an electron cloud around it. Why? You know, electron interaction, they repel. And so the electron coming close to another molecule that's nonpolar, the electrons there repel the other electrons away to generate a temporary dipole, a temporary interaction. The best analogy I can tell you is if you ever taken a balloon, okay, take that balloon and rub it on your head. By rubbing that balloon on your head, you had transferred electrons onto the surface of the balloon, okay? Now you take that balloon that you rubbed on your head and you bring it to your body. Well, on the surface of your body, guess what? You have electrons. And those electrons, as you bring the balloon close to your body, closer and closer, those electrons are repelled and kind of pushed away and going into your body, resulting in a partial positive area on your surface on your body. You have a partial negative area on the balloon, and guess what? That balloon attracts and sticks to your body. Okay. Obviously, that attraction is not permanent. It will eventually dissipate and the balloon falls off. But these are temporary interactions simply because these electrons are repelling each other as they get close to each other, okay? The bigger the nonpolar molecule, the more London force it has. And so you have a small, say, hydrocarbon, like say, maybe 6 carbon chain. You may have something like what's called hexane, 6 carbon chain. And then when you compare it to something that has maybe 14 carbon chain, a lot bigger, like a lot of fats, or have a lot of hydrocarbon chain, they have a lot more London dispersion forces simply because of their size. It makes sense, more electrons, more London force, okay? This is an example of what we're talking about, this temporary. So you get 2 molecules coming close to each other. The electrons on one side repel the electrons from the other one to generate a temporary dipole, okay? That's the important part. This interaction occurring right here in the bottom is temp, okay? It's temp because the electrons here are pushed away, these electrons in that direction, to generate a partial negative and ended up with a partial positive. So you get an interaction occurring here, all right? But it's only temporary. Eventually, the molecule goes back to more stable state, and that's where everything's going back to where it should be. Okay. All right, so dipole forces. Now this exists amongst polar molecules. Polar molecules have a permanent dipole, okay? Like for example, HCl. That is a permanent dipole. It has a permanent partial positive side and a permanent partial negative side due to the higher electronegativity of the chloride. Okay, so it's permanent dipole. And the molecule and the diagram here demonstrates that, not temporary like nonpolar molecules. So they are stronger than London forces, but they must be polar molecules, okay? Polar molecules in order to have that occur. All right, now hydrogen bridging forces. Hydrogen bridging forces only occur to those hydrogens that are bonded to the 3 elements, specifically fluorine, oxygen, and nitrogen, okay? And we have here an example where you have again, it's a permanent dipole, but the nature of the beast is such that this interaction here between the oxygen and the hydrogen that is bonded, this hydrogen is bonded to either a nitrogen or a oxygen or a fluoride. That's a very strong interaction here that's occurring, and that is called hydrogen bridging force, okay? Very similar to a dipole, the only difference being that is hydrogen bonded to either nitrogen, oxygen, or fluoride. NOF, right here to help you out. Not on file, maybe. Okay, so And then the hydrogen bridging force is another diagram of it. Stronger in dipole, but again, much weaker than ionic or covalent bonds, okay? Much weaker. But even at that, they do have sufficient strength that it's, you can notice the difference. And that explains why water has such a high boiling point, 100 degrees Celsius for water to boil. Whereas you have ethanol, which also has hydrogen bridging, but there's more hydrocarbon involved with it. And this boiling point somewhere around 78 degrees, quite different, even though both have hydrogen bridging. Okay, so the ion dipole forces, these are aqueous systems. We're talking about ions. So you have an ion in solution is being solvated by, in this case, water molecules around it. You have a strong partial negative due to the oxygen, actually two partial negatives on the oxygen, and they help solvate these positive cation of your ionic compound, in this case sodium. And then on the other side, on the hydrogen side, you have the chloride. So if this was, say, sodium chloride, well, the chloride negative would be on the other side, and that would be interacting. So you can see all these interactions all the way around, three-dimensionally, just this big giant matrix there, okay? All right. So summarize the difference in bonds versus forces, okay? So where we have bonds, we have ionic bonds, okay, which holds interaction between a metal and non-metal. We have polar covalent bonds where we have two nonmetals, but there's an unequal sharing of that bond. And then, of course, the non-polar covalent bonds, which again are two nonmetals, and there's an equal sharing between the same nonmetals, okay? Including carbon hydrogen, even though they're the same. Not the same, I should say. With respect to forces on the other hand, there's four forces. There's London, that once you identify a molecule as being nonpolar, automatically the only force they have is London forces, okay? Any polar molecule has a permanent dipole, their force is a dipole-dipole. And then only those molecules, I repeat, only those molecules that have a hydrogen bonded to either a nitrogen, oxygen, or a fluoride, only those molecules have a special dipole-dipole force. We're a little bit stronger, and that is called hydrogen bridging force, okay? And then finally, we have the ion dipole force, which deals only with a ionic compound being dissolved in an aqueous system, okay? Aqueous system, like being ionic, it has to be water. Okay, now, you may have a table that looks like this, and the question says, which has the strongest IMF in the samples of these molecules? Okay, but to answer that, we first have to define it as being polar or nonpolar. Now, if you go back to carbon dioxide, and sometimes you may need to use the Lewis-Dot structure. Remember when we did the Lewis-Dot structure? Okay, well, we did the Lewis-Dot structure on carbon dioxide, and we ended up with a formula that looked like this. You recall, okay? Then the next thing we decided was that, well, yes, there's a dipole between carbon and oxygen, but in which direction? It's going from the carbon to the oxygen because oxygen has a higher EN, electronegativity. Not only that, carbon dioxide has two of them of equal magnitude in opposite direction. Because they're in opposite direction, they cancel each other. The net result being that this whole molecule, though they had polar bonds, becomes nonpolar. Okay. All right. They're nonpolar. Being nonpolar, the only force they have is London forces. Now we have to learn to figure this out, because the next step is going to tell us, like, okay, so of these two, say carbon dioxide and PF3, who has the higher boiling point? Who has a higher surface tension? We'll talk about that here in a second. All right, Trifluorophosphorus Trifluoride. Okay, that compound, again, we use the Lewis dot structure to determine whether it's polar or not. And guess what? Just like nitrogen, it ends up with 3, a lone pair on the central atom. Yes, it has 3 polar molecule bonds, but that lone pair on that central atom automatically should tell you I'm dealing with a polar molecule. Okay. Now, here at this point, you have to decide, well, which one? Since it's polar, it cannot be London forces, okay? Cannot be. It can't be ion dipole because we have no ions mentioned here. No ionic compound, so it's in a covalent compound. It happens to be polar. So the only choice you have left is either dipole, hydrogen bridging. Well, we can eliminate hydrogen bridging. Why? Because there's no hydrogen here. So the only logical choice left over is dipole. Okay, dipole force. Notice the systematic approach we took here to determine what force to give it. Okay, no ions involved. Okay, it's not nonpolar. Okay, so I only got 2 choices, either dipole, hydrogen bridging. Hydrogen is not involved there, so the only logical choice left is dipole. Okay. All right, HF, which is like HCl, it is a polar molecule. Okay. Now, next thing you do, you notice you got hydrogen. Okay, so you might think, all right, I may be dealing with hydrogen bridging. So in order for it to be dealing with hydrogen bridging, you got to have either nitrogen, oxygen, or fluoride. In this case, you do. Therefore, it is hydrogen bridging. Okay, I state that because you may see like HCl. Okay, your first thought would be hydrogen. Okay, possibly hydrogen bridging. Let's go further. Is it nitrogen, oxygen, or fluoride? No. And the question is no. So the only choice here is dipole for HCl. Okay. All right, we have CH4. Even if you didn't know what that compound is, the fact that you see carbon and hydrogen only should tell you automatically you are dealing with a nonpolar species, okay? Simply because you're dealing with nothing but carbon and hydrogen. Being nonpolar, then the only force that's available for it is London forces. And then Ki, which automatically tells you it's an ionic compound. The only thing you can have here is it's ionic and polar water. And so the only force is the ion dipole, okay? So in order to define which force that molecule has, okay, you have to determine whether it's polar or nonpolar, or whether you're dealing with an ionic compound in the aqueous system, okay? Polar or nonpolar. And sometimes you need to take it a step further and determine the structure using the Lewis dot structure to determine the polarity of the molecule. All right. There's nothing to, we're not going to really talk too much about Coulomb's law. In fact, we can just really bypass it. Other to say that Coulomb's law, here's the equation. The only takeaway here is that, in essence, when charges come together, as they get closer together, obviously the charges get stronger. And I'm sure you've done this before, maybe with magnets. If you put the magnets either that attract each other or put them in opposite poles and you try to bring them together, you can feel that force really strong as the closer you get together. either the repulsion force or the attraction force, depending on how you set that up. And so what this is telling you is that that force is inversely proportional to the square of the distance between them, the radius. Okay, and it could be quite dramatic because it is inversely proportional. Meaning, when I mean inversely, means if I have two variables, I change one variable. If I do something to this variable and it goes up, the other variable drops in value, magnitude. That's an inverse proportional. Okay, a directly proportional means that if I increase the value of one variable, the other variable goes up proportionally, or non-proportional, but it goes up. Okay, and it could be quite drastic with the quantity. So that's the only takeaway really to remember about Coulomb's law. Okay. All right. Well, with this being said, well, so far the question here is, well, how do we define, how do we determine the answer to these questions? Well, first of all, read the question carefully. Are they talking about the intermolecular forces, or are they talking about the intramolecular forces? Are they talking about the bonds of the molecule, or are they talking about how these molecules interact with each other? And that is determined by how they write that write this question. For example, what holds the atoms together in one ammonia molecule? So here they say, what's holding the atoms together in one molecule? Nothing about anything else outside. So they're talking about what type of bond are we looking at? Well, the type of bond we're looking at is a polar covalent bond between the nitrogen and the hydrogen. Okay. Next is, what is holding sodium ions in water? All right, so now you have sodium ions, which is ionic compounds, and water, which are is a polar molecule. And so the only logical choice here is the ion dipole force. Okay, because we're dealing with an ion and we're dealing with a polar molecule, which would have the dipole force. What is holding three HCl molecules together? Now we're talking about interactions. We're talking about what is holding three molecules together. Okay, well, to answer that, we have to figure out the polarity of HCl, which we've done before, and is a polar bond. Okay, now once we know that, it is a polar covalent bond or molecule. Once we know the polarity of the molecule, you had to assign to it which force. Well, since it's polar, it is not dipole, it's not London bridges. Since sodium ions are not asking the question, we can eliminate ion dipole. So the only choice you got left is either dipole, or London dispersion forces, right? Well, to be London dispersion forces, it has to be hydrogen bonded to either nitrogen, oxygen, or fluoride. Here, hydrogen is bonded to chloride, therefore the only force available is the dipole force, okay? What is holding the ions together in salt? No mention of aqueous water, so we're not talking about an aqueous system here, we're just talking about solid salt. And we got sodium, which is a metal, chloride, which is non-metal. It's simply an ionic bond. It's holding the ions together. What is holding four H2O molecules together? So again, we're dealing with intermolecular forces. And we know that water is very polar. And so that means we have a specific force to give it because we have hydrogen bonded to oxygen. And the only force it has is the hydrogen bridging force. Okay. What holds the nitrogen molecules, gas molecules to each other? We're talking about intermolecular forces again. Nitrogen is diatomic. Okay. Therefore, it is nonpolar. And since it's nonpolar, the only force available to it is London forces. Okay. What is holding the oxygens together in an oxygen gas molecule? Well, that would be the bond between the oxygen molecule intramolecular forces. You want to know what type of bond that is? That is a nonpolar covalent bond. Okay. And then what is holding two ammonia forces molecules together? We have a molecule that has nitrogen and hydrogen, okay? And so the only thing here is hydrogen bridging forces, okay? Because it is a hydrogen bonded to nitrogen. Okay, this basically is summary is to determine the forces. You have the covalent bond. Obviously, if it's a covalent bond, is it polar, nonpolar? If it's nonpolar, the only force available to it is London forces. If it's polar, it could be dipole hydrogen bridging, well, or ion dipole. If we're dealing with ions, then the only force available is the last choice, or ion dipole. If we're dealing with hydrogen bonded to nitrogen or fluoride, then we got hydrogen bridging. Then all the other polar covalent compounds are simply dipole as far as the force that we can assign to it. Okay, now why do we want to do that? Well, we want to do that because we're going to look at three physical properties that are affected by the intermolecular forces of these molecules. Okay, now think of it this way. If I have two molecules that are holding on to each other very tightly, in order to break them apart, I gotta put a lot of energy into the system. So if the forces are very tight relative to the other type of intermolecular forces, it's gonna take a lot more energy to break them apart. Okay, we talked about the physical changes that matter undergoes. It goes from a solid, liquid, and gas. Okay, what we're doing there is we're not breaking bonds. Okay, what we're doing by putting energy into the system, we're causing the molecule to break apart from each other and to stop interacting as closely and as strong to each other. And so when we take an ice cube and we put energy into the system, those molecules that are in the frozen state, they're real tight. As we put energy into the system, they start to vibrate even more relative to each other, and eventually they separate from being in the solid phase and move into the liquid phase because we put energy into the system. If we continue to put energy into the system, okay, we will cause those liquid molecules to separate even further apart and go into the gas phase. All right. So the physical properties are like vapor pressure. Keep in mind what we just talked about. We're going to look at vapor pressure. Well, vapor pressure is this: your soda pop that has a cap on it. You have a container that has liquid in the bottom, and then up in the space, you have air. Well, some of the liquid has gone, specifically carbon dioxide has gone into that space area, okay? And if we keep it capped, we can, it could be a measurable amount of pressure, okay? So that is what we call vapor pressure of a liquid, okay? The boiling point, as the molecules are in the liquid phase, molecules are, still relatively together, but as we put energy into the system, they eventually move into the gas phase. So the boiling point is that temperature that converts that liquid into the vapor pressure. And surface tension is another physical property. Good example of that would be, when you get a liquid and you put it on the surface, sometimes that liquid, depending on the surface, depending on the liquid, would beat up more. Or, hold on. Okay. All right. Yes, yes, Amy, we'll do that. What time is it? I don't want to be talking too much, carried away. I want to stop here maybe about 10 more minutes, if that's okay with everybody. All right, let me get to a couple more here, and then we'll stop it here and we'll continue on Thursday. So surface tension is how well liquids beat up in the surface. If we put a liquid on the surface, depending on the type of force it has, it may beat up a lot or it may flatten out. It's much like when you wax your car and you put water in it, some of that water beads up. You got a dirty car like mine right now, I put liquid in there and that water spreads out. And viscosity is how thick something is. Honey and water, for example. Honey, we know, is very thick, so it won't flow very well, right, compared to water. And so that infers that the honey molecules are being held on to each other much closer, so they resist the flow much strongly than, say, water, okay? All right, so those are the physical properties we're going to deal with, and we're going to do a compare and contrast of molecules, and we're going to determine who's got the higher or the lower vapor pressure, boiling point, surface tension, or viscosity, and that's going to be based on the intermolecular force, okay? So I just talked about vapor pressure. This is a review of what we just talked about, okay? Okay, now, vapor pressure is the pressure exerted by gas molecules above a liquid in a closed container. So the stronger the IMF, the question to ask yourself, is it going to have higher or lower vapor pressure? So if the IMF, if the intermolecular force is strong, it's going to take a lot more energy to separate them. So if we were at room temperature and we're comparing liquids, the stronger IMF would have a lower vapor pressure because less liquids will want to go and escape into the gas phase, okay? An example would be here between these two diagrams of A and B, asking which has the weaker IMF. Well, that would be A, because having a weaker IMF, that means that those molecules readily go into the gas phase with not as much energy needed compared to B, which means that having more gas molecules in the air means that more pressure will be available and it'll have the higher vapor pressure A would compared to B.